Okay, in our last video, we covered the beginnings of exceptions and interrupt handling. One of the key points here is the code structure. So how the exception handler is laid out, both in memory in the N64 and in the ROM itself. So all kinds of kind of rules and different values and we need to get a grip of this because there's stuff. And once we've got some of the structure in place, we'll see that it's actually much easier to manage the code portion of this. So the first thing that we're going to do is we're going to take this template code, which is just normal ROM template, and I'm going to put it into my exceptions folder. And then I'm going to open all of these, and we'll start with the make, and the folder is just called exceptions, so we'll stick with that. And here I'm just making the length of the line match what's defined right below it. So pretty, yeah. All right, and so our make script is done. Our header is done. And now we have our template source code. And so again, we'll replace that name there. And this sets the ROM size. All of our normal stuff. We've got our standard includes. I'm going to go ahead and remove the graphics one. We're not going to be using anything from that for the majority of this exceptions and interrupt code. Other than that, very normal ROM. And just because we're going to one of the things, this file did not actually get renamed, so I'm just going to fix that, close it there, and rename here. And so the ASM is the only file that we actually need to have opened. That's what we're going to work with. So a quick note, one of the tools that I have added to my virtual machine that I run out of is XVI32. There's a lot of hex editors. Anything out there that allows you to look at a file in hex. It doesn't have to be complicated. Here, just I can show you. But hex editors are another one of those things where everybody has a preference, and that's fine. Use what you prefer. This one's been good for me for a very long time. And really what we're going to be focused on is the exact byte alignments of where everything lays down in the ROM to start with, and then we'll see once again how it lays down in the memory in the N64. So this video is going to be a little bit less on the assembly language side and much more on the BAS features and functionality for laying out these instructions in our file. So I'm going to close that, and here we go. So this is really basic. I'm in my exceptions folder, and it compiles, and it's going to run, but it's just going to run init and then go into its loop. So we've got a couple of different things that we need to deal with. So number one, okay, these are our rules. So we've got the TLB and then the general handler. Those are our two pieces. We've got this blob in the middle that we kind of have to deal with. And so our code's going to use these kinds of sections. So we're just going to kind of start. And we're down at the bottom below the loop. I'm going to throw in a few more knops just to make things a little bit easier. We're going to be doing a lot of code formatting stuff. So the first thing I'm going to do is use a line. I'm going to go ahead and go 16. This is a BAS macro, and we can actually see the definition to it. It's not magic. While the PC size is divided by the modulus of PC is greater than 0. It's not totally clear, but that's what it is. So the modulus being the remainder of that division. Write out a single byte as a 0. That's all it's doing. So we're going to say 16. So if the memory address is less than a multiple of 16, it's going to write zeros until it reaches that point, and then it's going to write down the next piece, the next thing that we're trying to do. Whether it's an instruction or an opcode or whatever that is. Okay, so our exception handler is in two pieces. Part 1 and part 2. And so this is at 0x8123.031c. And once again, I got that value from here. That's the first one. And then this is, of course, the first. All right. So this is... we've got some stuff going on. So the first thing that we're going to do is we're going to take this base directive. And this is going to be confusing. So follow along here. Okay, so the base directive, we covered this way back in, the first 1, 2, maybe the third video. The base directive is used for the branch and jump instructions, mostly the jump instructions, to determine what address needs to be there, because usually the jump just has a label. The label has to get converted to a memory address. So we need to know where the code is starting to execute from, and then it will compile the code that goes in there. So in this case, we're going to end up with these two different blocks of code, and then and so the first one's going to start, need to base everything off of this address, and this is going to need to, the second one is going to need to base off of that address. It will make more sense in a little bit, hopefully, but we do need to start there. I'm actually going to duplicate this. Once again, this will end up being two different compiled blobs, so there's going to be some duplication between them. But these are keyword things, BAS assembler macro pieces, and not relevant to the rest of what... they don't affect the actual instructions in the code. Okay, I said this was an advanced topic, and we're gonna get technical, and we're gonna dig in and write some some cool stuff here. All right, so we talked about that, those two different ranges, so that's good. Now, here's one of the other things, and this is a rather subtle piece, but the N64, when it boots up, one of the last steps that it does before it jumps into the game code is it does a DMA operation, but essentially it copies the first megabyte of the ROM from the cart into RAM, into the first megabyte of RAM. So that's a really convenient thing that the console does for us. But here's what is, if we ran this code as is, what will happen is the code that is in these two new exception handlers would actually be in memory in two places. They would be in memory at their correct address, the ones that we're defining here, because we're going to copy them here. But they would still be in that first megabyte of code, and they just don't need to be. So we're going to go ahead and use this origin directive, and we're going to put that up here. And I'm just going to work out what is 1024 times 1024, and we'll do that in hex. So this will be our origin value. And why, where will we see this? How do we know that this is working? When we look at here, right now we see the 1028, or approximately 1 megabyte. It shows in the file explorer here. And, well, to be fair, right now these won't actually contain anything. Let's talk about that first. So, if we go back to this N64 ink, I've got another macro, and this is one that I created, called fixed gap. And I'll show you how we use this and how this works, because it ended up much cooler than I expected and works great. So, fixed gap, it takes a base and then a gap. So, I'm going to actually step outside of the code that I'm working on, and I'm going to do this. So, I'm going to say gap test is my label, and I'm going to put in, I think it's a double of 0. And here, I'm going to say gap test. That's the name of the label up above it. And I'm going to say that it's only allowed to be 4 bytes. But this DD, I believe, should give me 8 bytes. So, what happens? And there we go. So, gap is greater than specified size. So here we have our error, and it points right to... well, actually, oh, there we go. So it points inside of our macro, where the error text is, but then it does say here on line 30, fixed gap test 4 is where our problem was. So that just works out great. So if I change this to 8 and recompile, it works just fine. So how we're going to use this is we're going to force data into this. Right now, this is 2 empty labels, which, if they're compiled right now, are going to have the identical value because there's nothing in between them. One option, of course, would be to come in here and just write a whole bunch of DWs or whatever else, but we're going to put instructions in here, and we're going to write code, and we don't want to keep track of DWs and those kinds of things. So what we do is we're going to take this and put it here. So this end label, just to be clear, is going to be handy for our DMA operation that we're going to do to copy the ROM, the exception handler from the cartridge memory space into the RAM, into the correct place. So that's really all that label is for. So here, we're going to take this, and we're going to say that, and we're going to do... all right, I got another little piece of magic here. If we go back and look at this macro, we can see this, defined debug show static value, and we've got a defined value, and so by default, the fixed gap macro simply inserts zeros. But especially when we're debugging this, how our instructions are going to lay out in the ROM, it's going to be nice to be able to identify them and see, did it go where I thought it would go? So we want to turn this on. So if defined debug show static value, and how we do that is we'll go ahead and do this up near the top, just so that it kind of encompasses everything. And so we're just going to write define debug show static value yes. And so that's good. And this is where it should get interesting. Okay, so we compiled. Now if we go and look, it's showing the same size, but there's only a few bytes difference in total. But let's take a look in our Hex Editor. And not, oh. There we go. A5 for a total of 8 bytes, right at the 1000 marker. And so again, I'm just going to kind of come back and I'm going to say, there is our origin 1000 marker. And we said, fill in this gap with whatever's not used. So here we said that it's going to be 8 bytes long. If we go back to our notes, we can see here that this is going to be 768 bytes. So we can take that and replace that value and make it again. And find our 0 address. But we should, there we go. So now we can see everything is there, right up to the 300 mark. So we've got a good count. We know where everything is. I'm kind of excited about that. That works out great. So now that we have that in place, I actually kind of want to do this. I'm going to take this same line, I'm going to put it there, and I'm going to take this one, and I'm not sure if anybody can predict what I'm going to do here, but 31C. So I'm going to take that, 0x31C, and but first I'm going to do a NOP. And again, this is just going to insert a 32 or a 4-byte, 32-bit zeros. At least I think so. And so this will give me... Oh. That will fail. No, that should be fine. Here, we're gonna get a little bit fancy. I am going to turn this off, I think, and then back on. I think this will work. Okay, so, you know what, did not go like I wanted it to. That's okay. Alright, so, I'm gonna just remove those. They're not doing anything. So, I'm gonna say DD0, DD0, DD0. Actually, here, I can do better. We have 1, 2, 3, 4, 5, 6, 7. I'm glad I didn't keep doing the DDs. So we have 7 words of data there. Oops. All right, and we're going to do this same thing here, only this is going to be based on part 2. And we have 228 bytes in this second section. All right, so I kind of did some crazy stuff. We'll see if we can make sure that this is clear. But the first, so from here to here should be 768 bytes with the A5 value right there. And then we're going to have 7 times 4, 28 bytes that are just zeros. We manually inserted those for the time being. And then this will check and make sure that we don't have too big of a gap there. And then down here, we're going to have another 228 bytes of the A5 value. And that's going to start at the 31C and run to just shy of 400. Should be 3FF. So we compile. And again, we're really just working with some dummy data. Those A5s are just filler to let us know that we're writing to the right place. And here we go. So what we have, right at the 1000 mark, we start and we show our A5s. And this continues on until we hit the 300 mark. And there are our 7 words of 0. Could be 8, but either way, that is our 31C address. And then we have so here it does look like we overstepped our 400 mark. So we want to take a look at that. And so this is why we're testing. So here we have another set of zeros kind of in the middle of nowhere here. And they run up to the 700 mark. I'm not sure, but I'm going to make this in hex. I don't know that it's going to make a difference, but I'm not sure. I just don't know. So we're going to find out. 228, we're just going to convert to hex, so that's E4. 0xE4. All right. So that points to exception handler 2, which starts at 31C for the base. Should also be 31C in memory. All right, so rebuild and reload. All right, well, we are still overshooting. So this sets the mark in our ROM file, our compiled output file. The align 16 should actually not do anything because we've got more than enough zeros on the end of the origin number. So this is kind of a dead code line, but we don't want to make a mistake, and we want to make sure that it's right for later. This is the executable address that it will be at. And so from there to there is going to be hex 300 in length. And then we have that end. And here we have, this is saying fixed gap, but it's actually saying the full 301C, and that is the problem. It should only be 1C, because that's approximately how long that is. Okay. And then we should be good. The E4, yeah, that was what it was. And then we verify. Okay. So there's where it starts. And scrolling down into the 200s. There's our 300 gap. Oh, we ended up with 8 words there. And this starts at 320. So we're off by something, but we're going to check the rest, and I think we'll be okay. And there we go. Oh, we actually bumped over by 1 there. So we have too big of a gap. So if we put in 1C, oh, the align 16 is coming into effect, and that is what is doing that, giving us that extra word. Trying to decide how I want to handle this. I'm going to make it 8. Well, you know what? So we're going to make this one F. Or should it be 2, 0? Then that will naturally align on the 16. And this will need to be 320. And we kind of waste one word, but this alignment step, DMAs have a restriction on the byte alignment that they can read from. And I forget if it's 8 or 16. So my plan was to go with 16. That's the safer of the two values and shouldn't have any problems. So I think this is the right thing to do. So I'm going to go back, recompile, and reload, and go back, go to our address. There we are. So again, starts perfectly. We knew that. There is our gap. It worked. Huh. Oh. Yeah, I think it worked. And I'm going to explain this in just a moment here. Because that looks funny. Like, it looks like we still kind of have our mistake in there. And we overshoot here into the 400. Okay, that was not what I was expecting. Oh, we didn't change that value. That's all. That was the only difference. Okay. Once again, I'm going to make this right. I'm going to verify it and then explain it. Okay. Perfect. Okay. So, if we come back here and we look at our code, here in this gap, we have our DW, we have 7 words of 0, which is exactly what we see here. But then we have our fixed gap. And so this fixed gap says it has to go to 20 hex, which is 4 more bytes than what is offered here. So in order to do that, it writes out the A5. So that word is written by this fixed gap macro. And that means that this and this fixed gap macro are now doing exactly as they should, going out for the length of E0, which because I don't necessarily think in hex 224 bytes. Before we were talking about 228. So that is perfect. And so that's where we're going to lay it down. So I'm going to come back, and one of the things that I started to talk about, but wanted to explain, okay, I think I covered it. Really quick, just in case. This 1 million in hex is supposed to be beyond the 1 megabyte that the N64 loads by default, so we only ever have one copy of the exception handler in RAM. It's not a ton of code. It's only 1, maybe 2K in total. But, you know, it's wasted space. Why have it? So we just pushed it up above that barrier, and everything looks good. All right. So we've actually got a few other set things that we need to have. And here's, we need to save our registers. So exception register storage. All right, so this is, I'm going to put in some comments here. So we have 32 scalar registers at 8 bytes each. Then we have 32 floating point registers at 8 bytes each. All right. There may be some other things, but I think that's the core of it. So what we're going to do is, so these are the DD0. This is divisible by 8, so 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 6, 7, 8. One more group. 3, 4, 5, 6, 7, 8. So 4 groups of 8 is 32. That's really all I was going for here. So we can, labels are free. So let's use some more. And so here, so I'm going to, again, we can use this fixed gap macro for everything. And here, I'm just going to do the math here real quick. Decimal mode, 32 times 8 is 256 bytes. So, and then here we're going to do floating point registers. All right, so, and again, this is going to, we're going to remove the gap test, and we can see our jump instruction and then a NOPS, and our register storage is going to happen after that. So this is a memory range that we want to have in RAM. And so that's kind of the big deal here. And so if we look again, just to point it out, the registers are saved below the 1 megabyte origin. So these are going to be in RAM, and other instructions will push it around, so on and so forth. But then our fixed gap macro will make sure that we always have that memory reserved. Our gap is larger than expected. And this is for our scalar registers. Line 70 is where it is. Yeah, so this one. All right, and so odds are, and again, that's there to protect us. 1, 2, 3, 4, 5, 6, 7, 8. I think we had an extra. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that should be better. We have a gap. Oh, and now it's in our floating point exceptions, our floating point registers. Okay, so we're going to do the exact same thing. 1, 2, 3, 4, 5, 6, 7, 8. And we do have an extra in that first group. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so there we are, and we compiled. And now we'll take a look, and again, so our code starts at the 1000 mark. We're only doing the init and then the jump loop, but I am not. Oh, at first I was expecting here. There we go. So this is a data byte. It treats it as a string, and it will convert it. And that will, because we used the 0 filler values instead of the fixed gap values, I was originally looking for that A5. Because we actually used zeros, they were just showing zeros in here, which was already the fill character, so it wasn't going to stand out. So we just changed that. We put little wrapper markers, if you will. So now you can see the SCRG right there, which was the scalar registers. And if we go out just a little bit further, okay, that feels like too far. Oh, there they are, floating point registers. All right, and so that is that marker there. And then nothing else until we hit the 1000 mark. And the cool thing is that this register location will just get pushed around. But as we have now proven out, this is not going to get DMA'd, besides the 1 megabyte bulk DMA at the start of the cart. But these kinds of things, it's just kind of nice to have them all aligned. All right, so that is our, wow, that is where our code is going to be. Kind of messy looking, I get that. But that is using the BAS macros to format and structure how that code is going to look in the ROM. And I am going to call this one a wrap. I'm really pleased with the result. I know it doesn't seem like much progress, but the next videos will take this, and this step here will it'll make sure that our code is right. It'll give us that compiler warning to let us know when something isn't right. And that's really the best that you can ask for. It's really easy to just spit out some bytes, and hopefully in the end you counted them right and did all those other things. But we could look and we could see that it was right. And that's a big deal. All right. Thank you so much. Be sure and check out the next one. We'll write some code.